In this video, I wanted to discuss the graph of tangent and the other three reciprocal trigonometric functions. Let's start with tangent and do a very detailed look at its graph and why it looks the way it does. And then we will do a quick look at the other three because they're quite tedious and, not quite as important as our main three, sine, cosine, and tangent. Also, on the exam, I'm going to mostly focus on having you guys graph sine and cosine as opposed to the other ones. I think the other ones are less so important to anything real that you would ever do in your life. But all the same transformational properties from sine and cosine that we were in the previous video can be applied to all of these as well. They just don't necessarily have the same terms. Like, for example, amplitude no longer applies to these, as you'll see. But let's start with tangent. So again, let's use a point plotting method and start with a trigonometric graph to try to do a very detailed, to create a very detailed graph of tangent as opposed to just a sketch as we were doing before. And just to review, as I define it, a graph is something where we're plotting points in a very accurate mannerism and actually being careful to do it very, very exactly. Whereas a sketch is just a rough graph. It's not exact. It's like these ones. It's a little bit sloppy, but it's illustrating the key properties and the key parts of the graph. So that's a sketch, but a graph, we're actually being more careful. Anyways, as usual, let's start with, say, 0 and then move from point to point to point to figure out what will happen with tangent. And we can also rely on our calculator, but we could start by creating a table of values. If we got x and y will be, well, what's the tangent of x? Much like we did with sine and cosine. So starting at 0. So returning back to our very basic definitions from prior sections, if we recall, well, cosine is y. So let's go back to our definition page. Cosine of the position is x, returns the x value. Sine of the position returns y. Recall that tangent returns the ratio of y to x. So when we're looking at the unit circle, we want to, tangent's going to return us a fraction, like for example 0 over 1 or 1 over 0. So as we're using the unit circle, we're going to keep that in mind. That by definition cosine tangent is going to be y over x. Again, not related to this x, doesn't have anything to do with it. So if we think about 0 on the unit circle, 0 is the initial location here, and tangent will, well, x is 1 and y is 0 at that location. So tangent always returns y over x for tangent of the current position. And again, I'm being careful over here. I'm using t because that's the terminal position based on the distance from the initial point. But at 0, we're at the initial point, so tangent of 0 will return y over x, which is 0 over 1, aka 0. So tangent of 0 is 0. Or we could also do these with our calculator, which we'll probably do. But I wanted to keep focusing on those definitions. I want to keep using them in class time because with reiteration, with practice, it becomes a little bit easier to understand them. If we kind of ignore all of that, we're not going to really understand how these functions really work. Anyways, let's say move on to pi over 6, because that's the next, point on our graph right here, as described before. And so, that will be our next value that I choose to graph on my thing. And again, if I want to try and define tangent pi over 6, I can do it over here. But it will return y over x. And remember, at that point, that was this point, which was the first point vertically from the initial point. Had a t value of pi over 6. But basically, y was 1/2 there. X was root 3 over 2. So the tangent of pi over 6 will return that ratio. And as I described before, that the 2's will cancel, and that will leave us with 1 over rad 3, which could be rationalized to be root 3 over 3. But basically, if we're trying to graph it, that's not very helpful. We want to know, well, what is the value of that? So let's use our calculator. And it might have been simpler if I was to just type it in to begin with. But as we described, obviously evaluating those trigonometric functions, as we did in 4.2, is super critical to understanding all of this. So that's going to be approximately 0.58 on the graph. And I could make sure that I did all that math right when I'm checking root 3 divided by 3. Perfect. So anyways, pi over 6 would give me 0.58. And on my graph, let's just say that this, like we did with sine and cosine, that like 2 ticks up is 1. That way I know 1/2 is right in between 0 and 1. And so tangent is a little bit more than 0.5. So the first point on tangent will be right there. Okay, neat. Well, what's going to happen? Say, for example, I was to go to the next point. Say, for example, pi over 4 or pi over 3, those same points on the unit circle. Well, actually, if you remember about pi over 4, which is going to be right here on my xy graph, that's the point on the unit circle which was directly in the middle, right there. And if you recall, pi over 4 was the location right in the middle where both x and y were root 2 over 2. So the tangent is going to be that ratio, root 2 over 2 divided by root 2 over 2. Since it's the same thing, it's going to make exactly 1. And this is another value, one of those special points that's kind of important to remember. Tangent of pi over 4 produces exactly 1. And pi over 3 is the next point, which on our unit circle would be pi over 6 has an x value of 1/2 and a y value of root 3 over 2, which will have a ratio of root 3 over 2 to 1. Exactly the reverse ratio of tangent at pi over 6, because it's the flip fraction. Let me go ahead and note that work for what I'm saying, so it's easier to follow what I'm doing. So at pi over 4, we had root 2 over 2, oops. It was x over y, which was 1. And at tangent of pi over 3, we've got the reverse ratio root 3 over 2 over 1/2, which the 2's will cancel, giving root 3 over 1. Root 3, which is approximately 1.7. Just make sure. And as I was saying, you could technically do all this math with your calculator. We will stop doing it manually very soon, but reviewing the sense of how tangent works and why it will graph the way it does. But the next point is one that you might remember is kind of weird, because when I get to the very top of the unit circle, the problem here is that, well, x is 0 and y is 1. So if I'm trying to do the tangent of pi over 2, the problem is I get, well, y is 1, x is 0. That is an undefined ratio. So as we, as I mentioned when we were talking about tangent before, this is not okay. And all that means is that this is not within the domain of the tangent, aka it will not graph. But what this actually does to the graph is it creates a vertical asymptote much the same as it did with rational functions when we were dividing by, say, x plus 2. So anytime we're not allowed to divide by 0, that creates weirdness in the graph. But basically, let's go ahead and draw these on our graph to manifest all of this information. At pi over 4, we had it was exact, tangent produced exactly 1. At pi over 3, which is the next major tick mark before pi over 2, tangent produced about 1.7. And by the time we got pi over 2, we ran into a problem, which, as I mentioned, created a vertical asymptote. So for now, I'm just going to put that right there. But this is going to occur. But what will happen with the tangent is it starts at 0. Oops, let me use black there. And it's going to move upward, passing through 1, going up to 1.7. What will actually happen is it will, as the tangent approaches pi over 2 from the left-hand side, it will actually blow up towards infinity, because what will happen is we're getting closer and closer to 0. And so let me try to explain why that's going to happen. Because on the unit circle, as we're getting closer and closer to this point represents a position on the tangent function where that ratio is undefined. Also, what tangent does is it produces the slope of a particular line, of the line if we were to connect that point back to the origin, where the initial point starts with a slope of 0, then it moves up to a slope of 1, then a slope of 1.7, and it will get steeper and steeper and steeper. And if I'm thinking about graphing the value of the slope, up to the point where it hits the top, what we get is an undefined slope, which is what happens when you're trying to find the slope of a vertical line. We say that the slope just doesn't work, but as you get closer and closer, the slope will get steeper and steeper and steeper. Technically, it will become infinitely steep as you get closer and closer. Like, for example, say I was to try a point right here, like right before pi over 2. Pi over 2, just to throw some numbers into this, is approximately 1.57. Let's say I was to check the tangent of 1.5. Since this is 1.57, 1.5 would just be very close to it and would have a very steep slope. But my point is, let's say I was trying to figure out the tangent value at right here, 1.5, which it becomes very, very large. And as you get closer and closer and closer to 1.57, let's try 1.56, it will get increasingly large. And that's the behavior that I'm trying to describe here, which is why tangent has a vertical asymptote. And then once you get to exactly tangent of pi over 2, again, you could try it with your calculator if you wanted. What will happen is it's a domain error because it does not work. But my point being is that as you get closer and closer and closer to pi over 2, it will continue to get large and infinitely large. There is no limit to how big it gets. But basically, tangent will blow up towards infinity, which, you know, reflects in its limit. And then continuing along this trend, let's actually from here on out graph the rest of it, but tangent will actually repeat itself. On the right-hand side, it will come back down, and every midpoint it will always be at either +1 or -1 due to its cyclic behavior. So I'm gonna denote, and I'll try to explain them as I'm going, some of these key points that I know are on the graph of tangent. But it will, once I get to pi, it will repeat itself, and it will have another vertical asymptote at 3 pi over 2. And I'm gonna talk about this as we go back to the unit circle. But on basically, tangent will go up, and then it will come back down. It will blow up towards infinity. On the other side, it will come down from infinity back up to 0. It has a very similar cyclic nature to sine and cosine. But actually, what is one different thing about tangent is its period is not 2 pi. Its baseline period is actually pi, meaning that over the course from 0 to pi, it completes one. It's not really a wave, but it completes one cycle. Then it will blow back up again and come back down, as the tangent will. And it will continue doing this forever, just like how sine and cosine are really wave functions that go up and down forever. So does tangent. And if you create a basic sketch in a trigonometric window of the tangent, you'll see what I mean. But basically, it has this shape to it. It's a very, very unique, interesting shape. It's sort of like a rational function that has little noodly things, but it does little noodly things over and over and over forever, which, you know, kind of strange. But the key thing about where the vertical asymptotes are is they're always based on the period, and they're always based on where it is undefined. Like, if you're wondering how did I know it had a vertical asymptote at 3 pi over 2, it's just because that's another point that if we look at its tangent value, the tangent at that point would be y over x. It's another part where it's divided by 0. So at those 2 points, that's where it's going to run into those problems. But as I'm going up, the slope gets larger and larger. But as I move over here, the slope becomes negative. It starts at a very large negative slope, goes down to 0, and then becomes back to a positive slope. Again, thinking about connecting that point to the axis. And then it becomes undefined again. Then the slope goes back to a negative slope. And that's kind of why tangent dipped down to negative down here, back to positive after all is said and done. And actually, let me go ahead and note that last value here. What I think is the easiest way to graph tangent is start with the vertical asymptotes, as was my recommendation for rational functions, right? Because those are the weird spots. Once we have the weird spots, we know what tangent does in between it. It has sort of a noodly shape. And in the next few videos we'll talk what about the other three, secant, cosecant, and cotangent, because this one is already way long enough. And Thanks for listening.